So with quantum numbers are, you're using three values to describe one of the specific orbitals in your electron configuration or orbital diagram. So you also have a fourth quantum number that describes an individual electron in an orbital. So what you want to think of quantum numbers as is an address for each electron. Every single electron in every atom, it has its own unique address. So there's going to be some numbers that you're going to see multiple times, but there's only one combination for a certain electron. So n is the principal quantum number. That's the title of it. I'm never going to ask you to specifically talk about the principal quantum number, but this is the first value in our address, if you want to think of it that way, and it corresponds exactly to the energy level. So if we had an electron in the 2s sublevel, the energy level for it would be 2. So that would be our first quantum number. The other way to think about quantum numbers is like a GIS coordinate or GPS coordinate. You're giving these four values so you can specifically locate the electron inside the atom. So the second term is the azimuthal. It's described by a script L. This term describes the shape of the orbital. So this is just like this is referring to the sublevel. The only difference between before and now is that we're going to use a number to describe it rather than a letter. So instead of an S, we'll use the number 0. Instead of a P, we'll use the number 1. Instead of the D, it's going to be the number 2. And then instead of F, it's going to be the number 3. The next one is an M sub L. It's an M with a subscript of the script L. It's the magnetic quantum number. What this is describing is the specific orbital. So just like before, we didn't really have a term to describe each orbital. Now we do. Now we have a specific numerical value describing each orbital within. So for example, in the S sublevel, which we would describe as the term 0, the M sub L, or the magnetic quantum number, is only 0. So the P sublevel, we have 3 orbitals, so we go from the -1 to the +1. So what we're doing is we're essentially pulling the L, going from -L to +L, and it happens to correspond with the quantity of orbitals within specific quantum values. So what about F? F is going to go from -3 to +3. So it's going to be -3, -2, -1, 0, 1, 2, 3, which has 7 values. So this is where that logic is starting to come into play. This is this specific value, I think, is the hardest of all of the quantum numbers to figure out. But it's based off of the previous ones. And then the last quantum number, or the quantum value, is going to be the spin of your electron. This is the easiest one. We have referred to up to this point as positive spin and negative spin. Well, with this value, what we're going to do is the positive spin, we're going to assign the +1/2 value, and the negative spin, we're going to assign -1/2. So if you don't know how to do any of the other ones, this one, you have a 50-50 chance at getting it right. We always start with the positive spin for the first electron in a specific orbital, and then this negative spin is the second. So we're going to go through some examples. I'm going to pull up a periodic table to make it a little bit easier to talk about. So our first question is asking for the 8th electron in argon. So if we're taking a look at the periodic table, argon is located right here. It is a noble gas, as we already know, but we don't want we want the 8th electron in argon. So how do you figure out what the 8th electron is? Well, you really have to count. So You'd start with your 1s, so that would be my first electron, second electron. After the 1s, I'd go to the 2s, third, fourth, 2p, fifth, sixth, seventh, eighth. So this electron, this downward facing electron, is my 8th electron. This is the electron that I need to figure out the quantum numbers for. So each of these electrons has its own unique set of 4 quantum numbers. We just want one specifically. Where this comes into play is when you're counting. So when you have a p or a d or an f where you have multiple orbitals, you have to be careful when you're counting your electrons, because you always add 1 electron to each orbital before you begin pairing. So right now, without doing anything else, we already have our first 2 quantum numbers. So our first quantum number is the energy level. Usually it's written in kind of parentheses for us. So it's the energy level, which comes right from out in front. So this is the second energy level. We are in the p sublevel, so that's our second quantum number. P has a number of 1. S is 0 if we had S. And we can figure out our fourth quantum number. Is it a positive spin? Is it an upward facing arrow? Or is it a downward arrow? So it's going to be -1/2 because it's a downward facing arrow. So we have all the quantum numbers except for the third one, which is the magnetic one, which represents the orbital. How do we go about assigning a specific orbital value? Okay, so we're going to go -L, which is 1 for us, to positive L. So we're going to start with the -1, 0, positive 1. I just assign each of the specific orbitals a value. So in this case, my third quantum number is -1. So now that we have the quantum numbers, this is for the 8th electron. Okay, argon has 18. I'm going to tell you a secret. Okay, it's really not a secret. When we stopped at the 8th electron, it was the same as the electron configuration for oxygen. So even though it's the 8th electron in argon, it's really the last electron in oxygen. So sometimes, like this problem, they'll just ask you for a random number of electron in some compound. You don't have to draw out the whole electron configuration. What you can actually do is find that number, find the atomic number on the periodic table, and then write the orbital diagram for just that small part. So if you take a look here in the 2p, I need 1, 2, 3, 4 electrons. Granted, it was number 8. Number 8 is pretty easy to count to, but sometimes it could be number 78. Do you really want to count up to 78? Probably not. So what we're going to do in the next example is find the 4 quantum numbers for calcium, which is the 20th electron in calcium, or the 20th electron in whatever is more than 20 electrons. So calcium is the second electron in the 4s. So I would have the 4s orbital diagram. It's going to have 2 electrons. So that tells me that this second electron is the downward facing electron. This is the one that I want to find an address for. So we already know our first quantum number is 4 from our energy level. Our second quantum number is going to be based off of the sublevel, which in this case is 0. S is 0. We only have one orbital, and in S it can only be called 0. -0 to +0 is the same thing. You can't have negative, positive, 0. So it's just 0 with -1/2 as our spin. So anytime you have something in the S block, you're going to have a number, 0, 0, and then either +1/2 or -1/2. So the S block is kind of the easiest one because you're really only looking at 2 of the 4 values. So let's try silver now, which is in the D block. So this part of the periodic table is represented as 4D. 4D has 5 orbitals in it. So silver is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. Now, if you remember back to when we were talking about exceptions, silver is actually an electron exception because it's in the copper group. So just to do the noble gas configuration really quick here, it would be krypton and then 5s1 and 4d10. So because of that kind of odd difference here, the 47th electron would really be the last electron in the 4d because we skipped one in the 5s. This is only for the silver group, which has copper and gold in it, as well as chromium, molybdenum, and tungsten's group. So it is a bit of an odd one. We'll do another D block one just to help clarify this. So we're going to fill our D with 10 electrons, and the 10th electron is going to be the one we're determining quantum numbers for. So it's going to be this one right here. So we already know we're in the 4D, so it's going to be 4 is our first quantum number. D is 2. So then the EMS of L is going to be going from -2 to +2. So in this case, we'll have a +2. So I generally, if it's a positive number, I like putting the positive number here because the third quantum number can be positive or negative, and it improves communication. It also reminds myself that this one should be positive or negative. It doesn't have to be positive. And it was a downward facing arrow, so it's -1/2. So like I said, silver is a little bit of an oddball because of its difference in orbital diagram or electron configuration, just because of the way the energies work out. So let's try nickel. It's right next to that copper group. Nickel doesn't have an electron exception, so we are going to be in the 3D block where we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So I'm going to add 8 electrons. Remember that I add 1 electron to each before I go back and begin pairing. So that was 1, 2, 3, 4, 5, 6, 7, oh, need one more, 8. So this is the only electron I'm worried about right now. It's the 8th electron. Now what a question could ask you is to write the quantum number for all of the electrons in nickel, which would be 28 combinations of 4 numbers, which is another way these questions can kind of work. So what we're going to do, we're in the 3D block, so our first quantum number is a 3. The second one is 2, because we're in the D block. So then the EMS of L, we go from -2 to +2. So our third quantum number is going to be 0. Remember, we can't have a positive or a -0, it's just 0. And our last quantum number is -1/2. So we're going to do an F block element. We've picked number 98, which is californium. So this is in the F block. This happens to be 5F. Remember, 5F has 7 orbitals. So we would just count 1, 2, 3, 4, 5, 6, 7, 8, 9. So we need 9 electrons. So I'm just going to add all of my ups. Remember, we go up, 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 up before we start having downs. So we have 7, 8, 9. So that's the electron that I'm focused on. So we know it's 5F. So my first quantum number is 5. My second quantum number is 3 because 3 represents F. You can remember the numbers because it goes in the order that you have. S is the first thing you start with, so it's 0. P is 1. D is 2. And F is 3. So 5, 3. So then we go through starting with -3, -2, -1, 0, +1, +2, +3. So we are at -2 here. 5, 3, -2. And then it's a downward facing electron, so it's -1/2. And I'm done. Okay,